Let us go through a brief introduction to some formal aspects of quantum mechanics. We will keep it a non-rigorous introduction in contrast to a complete course on quantum mechanics, but it is nevertheless necessary to digest some simple but very important formalism and symbolism, since it will continue to emerge frequently here and there, and it is that kind of representation, mathematical representation, that you will encounter throughout all textbooks on quantum mechanics. So let us turn our attention back to the concept of the wave function. We consider it to be continuous for the position in space of a particle. And its value, the density probability or the integrated probability function of the particle in space, which gives us the total probability that an event occurs, this does not change abruptly from one point to another. For the case of the position of a particle along an x-axis in space, it is a continuous function. That is, the wave function psi of x, psi x or psi x, is a continuous function in x, technically speaking. The system has an infinitely many degrees of freedom, one says also. Infinite many degrees of freedom. We saw, however, that there can be other behaviors of quantum systems. For example, that the energy state of atoms is quantized. For instance, recall the optical spectral lines of hydrogen or the Frank-Hertz experiment, where we saw that the atoms have discrete energy levels. Here, the wave function can no longer describe the behavior of continuous energy output, but the energy is in steps. So also the wave function can no longer be a continuous function, but must be represented by a set of discrete possible states of the system. As, for instance, we have already seen in the case of the hydrogen spectrum. In these cases, we must write the wave function psi not as a continuous function in space, but as a set of single states, E1, E2, E3, and so on until En, the nth energy state, which can be represented, which can represent the discrete energy states, capital letters E1, E2, E3, and so on until En, or the dynamical variables like spin or angular momentum, as we shall see later. In the language of quantum mechanics, each of these discrete states of a quantum system are called Eigenstates, from the German Eigen, which means self. Eigenstates are those quantum states where repeated measurements of the system under consideration will always lead to the same result. So, for example, if a particle is in a specific eigenstate, energy eigenstate, this means that I measure its energy and I get always the same energy. So then we can say that particle is, or that atom, or whatever, that quantum system is in that eigenstate, which distinguishes itself from other sort of states that we will see later, because we will see that how also quantum systems can be also in a superposition of states. So, for example, the energy of a quantum system is the dynamic variable, the observable quantity that can be measured, and which can have several discrete eigenstates, E1, E2, E3, but not something in between. In quantum mechanics, these eigenstates are defined on a Hilbert space. Without going too much into mathematical details, it suffices to say that the Hilbert space is an abstract vector space that is an extension of the real Euclidean space to a multidimensional space of complex numbers and complex vectors. If the Hilbert space has a finite dimension, it is the state space of a quantum system with a finite number of eigenstates. Otherwise, it is infinite. As infinite is then the number of degrees of freedom. Another important difference between a space as we conceive it in school geometry is that the elements of a Hilbert space are no longer points and coordinates, but functions, the wave function being the primary object to act on. So instead of points, we have wave functions. The eigenstates E1, E2, E3, and so on form the eigenbasis of the Hilbert space, and the overall possible states of a quantum system are represented by a vector defined on this eigenbasis, called the state eigenvector or just eigenvector, or simply the state vector. As in the figure you can see a simple case for a system with 3 possible eigenstates. So you see here, for example, the case of a system with 3 possible eigenstates. Therefore, we can depict it, make a graph, a picture in a 3-dimensional space. If it would have more eigenstates, more possible states, it would be impossible to make a graph of it, because then we would have a multi-dimensional object. However, until 1, 2, or 3 dimension, it is still in our human understanding how to represent this with a graph, and it resembles in some sense the Cartesian coordinate system. However, instead of the x, y, and z axis, we have the axis corresponding to the 3 possible states or eigenvectors. Whereas the length of each eigenvector, take for instance E1, is given by a complex coefficient C1. The same also for the other 2 vectors C2 and C3. These are complex numbers which express how long this vector is. Whereas here the total vector, so to speak, which is a state vector in quantum mechanics, is the linear combination of all the eigenvectors. So we see that this is given by the red vector, and we see that the state vector of the system over all the possible states is given by psi equals C1 E1 plus C2 E2 plus C3 E3. We will now quickly describe also this formalism with the strange brackets. I will come to this next. But what is important that you understand, at least intuitively, this principle of the state vector and how this is a linear combination of all the possible eigenvectors in what we call a Hilbert space, in this case a 3-dimensional, but normally it is a much bigger Hilbert space, eventually also an infinite dimensional Hilbert space. So as we see, let's recapitulate, because this is also an important point. The information with what probability each of the eigenstates will be observed after a measurement is carried by the complex coefficients C1, C2, C3, and so on. This means also that the Born rule still holds. You remember modulus squared. The probability, capital letter P, associated to the E's eigenstate EI is the squared modulus of the E's complex coefficients CE. So as we read it here, P of EI equal CI times CI complex conjugate is equal the modulus square of CI for I equal to 1, 2, and so on, depending from the dimension of the Hilbert space, or if you prefer, the number of possible eigenstates of the quantum system. So let us see something about this notation. The notation of this sort here, and which is pronounced ket psi, is common notation for vectors in quantum theory. State vectors can be written according to the Dirac notation. Paul Dirac was a British physicist who made several contributions in quantum theory. We already saw how he used to write the kind of integrals we encountered when we discussed the Born rule as brackets, as, and you pronounce this here, bra psi ket psi, sort of. Each bracket is a product, more precisely one should say the inner product, of a bra vector, bra A, a row vector, which elements are the complex conjugate of A, and a ket vector, B, a column vector. As you can see, Dirac wasn't lacking a bit of weird lexical fantasy, which however turned out to be extremely useful. For example, the general bracket bra A ket B is given by this formula here. Here you see bra A ket B is equal the complex conjugate vector of A, bra A, which is written horizontally as A1 complex conjugate times A2 complex conjugate, and so on until AN complex conjugate, times the vector, the ket B, which is a vector written vertically and in each element without the complex conjugation, so B1, P2, B2, and so on until Bn, and which finally is written as A1 complex conjugate of E1 times B1 plus complex conjugate of A2 times B2, and so on. This is just an algebraic method to compactify our writing. So you see the right expression of this formula can be synthesized in this very compact form, bra A ket B. This means also that with Dirac's notation, a lot of calculations are made formally simpler. For example, if you take this one here, the bra of the E's eigenstate, bra A EI, equal to a vector which is 0 everywhere except at the CE's coefficient, at the E's coefficient, and you put there the complex conjugate coefficient corresponding to the length of the E's eigenvector. So you have 0, 0, 0, and at the E's position CI complex conjugate, or CI star, and the others also 0. And then you write as a psi equal C1, C2, C3, and Cn, and then the probability to find the E's eigenstate can be written also in the bracket notation as follows. The probability P of EI, the E's eigenstate, to measure the E's eigenstate, is given by the modulus square of bra EI ket psi, and which is equal the modulus square of CI, and according to the little formula and calculation we have done here above. It is just a symbolic formalism introduced by Dirac, and later developed further by others such as the mathematician John von Neumann, with which one represents the probability to observe a system with a number of possible discrete states. It is customary also to state that it is the modulus square of the projection of the state vector psi onto the eigenbasis spanned by its eigenvectors. One can interpret the dashed lines in the graph as projections here. These dashed lines are the projection, are what the measurement does. When you measure a quantum system, you project its state or state vector onto one of its eigenbases. It is the measurement act that projects the state vector onto one of its possible eigenbasis vectors. This is analogous to the wave function collapse or state reduction we saw in the case of a continuous wave function. There also the act of measurement collapses the wave function describing the particle position in a continuous space on one of the infinitely possible states. After all, also the position of a particle is a state. Here the same happens. The projection of the state vector onto one of its eigenbases is, mathematically speaking, what we do in the reality doing a measurement in the laboratory with a measurement device. We bring the quantum system from a quantum still not defined quantum state and then make a measurement, and only one of these possible states happens to come into being, so to speak. Moreover, once the quantum system has been placed into one of the eigenstates, in the quantum mechanics jargon, one says it has been prepared into a specific state, and if it does not interact with the environment, then every subsequent measurement will always deliver again the same result. Therefore, the system being in the state ket EI. Again, with the sum of all the modulus squared complex coefficients, each representing the probability of the ith eigenstate to be measured, these must obviously sum up to certainty. That you must get one, number one, which tells us that this is 100% probability that this one of these must come out, because there are no other left. Or to put it another way, the sum of the probabilities of all possible events must give unity. No? Note how the sum of all the probabilities adding up to unity is represented in Dirac's notation neatly as this expression here, which is the modulus square of the bracket of psi, which is the sum of all the complex coefficients squared, and which must finally give the number 1. Now, what do physicists do with all that? The point is that if we want to deal with real-world measurements, we must specify which information from this mathematical construct, the wave function or state vector, we want to extract. That is, which physical quantity, more precisely which dynamic variable, we want to measure. Among them, for example, the position, momentum, the energy, the angular momentum, and so on. What mathematicians and physicists do is to define an operator which, as the word says, operates on the wave function or state vector to extract, to project, to obtain a specific piece of information associated with the observable. Examples of mathematical operators every one of us knows are the addition, subtraction, multiplication, and division operators, for example. The multiplication operator acts on two quantities, A and B, to obtain another quantity, C, as A times B equals C. That's simple as that. This is the meaning of operator. This point is an operator. Similarly, one can conceive of a more abstract operator, let's call it O, acting on a state vector psi. If we consider this operation as a formal equivalence with an act of measurement of a dynamic variable, that is the observable of a system, the output of this operation should tell us something about the outcome of this measurement, and which is always a number, a scalar quantity, and which usually we will call always lambda, a number, which represents the expected value from this measurement, the so-called eigenvalue. And you write that the operator O operates on the state vector psi and gives is equal lambda times psi. Lambda, the outcome of a measurement, or more broadly, simply an observation. It could be, for example, the position of a particle. Lambda would be then, it is in position at a position in 3 centimeters in some reference system. This equation is therefore called the eigenequation. The eigenequation. It is the mathematical procedure we have to perform in order to make predictions once we know the experimental setup and the boundary conditions. Stated a bit more precisely, one should say that each dynamical variable, for example position, momentum, angular momentum, energy, and so on, is associated with an so-called self-adjoint operator. The observable, the operator is the observable associated to the dynamical variable that acts on the state vector of the quantum system psi, and which furnishes a scalar quantity, the eigenvalue lambda. I said self-adjoint. Well, this is not so important. Self-adjoint means that the complex conjugate of the operator is again the operator itself. But these are mathematical aspects that are not so important for our purposes here. Simply remember the connection between the classical notion of dynamical variable and its counterpart in quantum mechanics as operator, the observable. To avoid a possible source of confusion, let us state this again from another perspective. Operators are not numbers. 1, 2, 3, 4, 5, etc. are numbers, whereas plus, minus, multiplication or division are binary operators. Binary because they combine two numbers called operands to obtain another number. For example, 1 plus 2 equals 3. Therefore, it makes no sense to state that if an operator acting on a state function psi is equal lambda times psi, or ket psi, the state vector, then we can equate O equal lambda. This makes no sense because you are then equating an operator with a number. And we have said these are two distinct objects. That is, one is mistaking apples for bananas. So this distinction must be clear in our mind. Moreover, the operators used in quantum mechanics operate on functions rather than on numbers. Perhaps the simplest non-trivial unary operator is the derivation operator, d over dx. Unary because it operates on one function to obtain another function. For those who know how to take derivatives, for those who do not, don't worry, we will not need them anymore. An example could be the derivation of the exponential function e power 2x, and which gives 2 times the same exponential function, 2 times e power 2x. But nobody would equate the operator d over dx and say this is equal to. The operators as one thing and the numbers are another thing. Operators act on functions and obtain another function. Whereas there are also these binary operators we use in our daily experience, plus, minus, etc., which work on on numbers and again obtain numbers. But in the quantum operators act on functions and obtain functions. And these quantum operators, that is observables, are also called, by the way, Q numbers, because they have a formal analogy with numbers. But remember that they aren't numbers at all. Once that has become clear, here are some examples of observables. So, for example, in the classical world, we have the position x, whereas this, here we have an example of an observable. The simplest one is the position operator, and just we say that the operator for x is thus some operator x, which acts on the wave function and will give me the position of the particle if that wave function is the description of the quantum system. If we want to know the position of a particle, therefore, we have just to multiply the wave function with the position variable x and then take the modulus squared to obtain, as usual, the probability density in function of x, and which tells us something about its whereabouts. The momentum operator, that is the observable which tells me something about the momentum of the particle, has the form of a derivative operator. And it is given by this derivation operator of over a function, where d over dx, times some constant. It will turn out in quantum mechanics that it is minus I times h bar, where I is the imaginary number, h bar is the Planck's constant divided off by 2 pi. Where this comes from, this would need all a mathematical introduction, and we would see why this is. The important point is that you recall that to momentum in classical mechanics, which is just mass times the velocity, in quantum mechanics you must no longer think as dynamical variables in classical physics, but as operators, that is, observables. And one operator is the derivation operator that you may have learned when you have learned a bit of calculus, if you didn't take a look at the appendix and where we discussed also this aspect. Taking the derivative in space of the wave function, therefore, times the Planck constant bar and an imaginary number, will furnish a mathematical expression that tells us something about the speed of the particle that the wave function describes. So similarly, the energy operator, which is called the evolution operator, or also Hamiltonian, has a bit more complex structure. It is given by a second derivative in space times minus h bar squared over 2m, where m is the mass of the particle, plus a function v of x, which represents the potential energy of the particle. So we have the operator, the Hamiltonian, h is given by this quantity here, and this is nothing else than an operator which, if it operates on the wave function of a quantum system, it will give me as output the energy of the system, or the possible energy states of the system. It is in particular this latter observable which leads to the famous Schrödinger equation, which in a compact form can be written here as h operating on the state vector psi is equal the energy eigenvalue E, here in capital letter E times psi. This is the eigen equation for the energy state of a system. Once the wave function or the state vector describing the system is given, one applies the Hamiltonian as prescribed by the eigenequation, and we will obtain as eigenvalue E the energy of the state. The Schrödinger equation is so important because it helps us in obtaining the energy states of any quantum system at the energy levels of atoms and then nuclei, or even more complicated objects like molecules. Let us make only a brief insertion here that will turn out to be important later. Another important quantity in quantum mechanics is the so-called expectation value of an operator. That is, the average value one obtains by measuring an observable many times. It is operatively a fundamental notion in quantum mechanics because in the laboratory what one usually must tackle in the real world are average measured values. For example, for the position operator x equal small x of a particle, one integrates its position x, weighting it by the probability of finding it in x, or in analytical terms, you can see here it is the integral over all the space, if you wish, over all the universe, of the wave function psi x times the position x times psi, the complex conjugate of the wave function itself. It is the average value of the position x of a particle that one expects to obtain after a large number of measurements. More generally, this can be written in more compact form by using Dirac's notation, stating that the expectation value of an operator A, let's call it just with a letter, capital letter A, in state psi, is defined as the bra psi, the operator A or A, ket psi, as you can see here, with the right hand side Dirac brackets as defined in the integral above. Now, turning back to Schrödinger's equation we saw previously, this is, however, not the most general equation, because this was the time-independent Schrödinger equation, while physical systems are, in many cases, time-dependent. There is a factor of time working. As everything in the physical world, it evolves according to time, and we express this by a time-dependent function. Therefore, the time-dependent energy operator is called, there exists also a time-dependent energy operator, and which is called evolution operator, and is given by this quantity here. So we generalize the Hamiltonian to a time-dependent operator, or a parameter, to a time parameter t, and which is h of t equal a quantity, which is again an operator, the imaginary number times h bar times the derivative operator over time, d over dt. That's why you will frequently find the time-dependent Schrödinger equation in this form here. You have the Hamiltonian, that time-dependent Hamiltonian, who acts on the state vector psi, ket psi, equal I h bar d over dt over the same ket vector. This is again the time-dependent eigenequation, so to speak. The Hamiltonian operator also defines the time evolution of the wave function from a time 0 to a time t. In particular, if h is independent of time, so therefore we write h without the time parameter, given a state psi 0 at time 0, we have the state vector at time 0, at an initial time t equals 0, the state of the quantum system ket of psi of t at any subsequent time t is generated. It is in quantum mechanics, you say it's generated by the so-called unitary operator, which is this quantity given here and is expressed with the exponential. The unitary operator u, capital letter U, equals e exponential minus I h t over h bar. And using this quantity, applying this operator onto the initial state vector, initial in time, u operating over the ket of psi 0, this quantity here, then you obtain the state of the system at a subsequent time t, that is the ket of psi t. So this quantity, this equation here, tells me how psi, with initial state psi 0, evolves, develops in time and becomes psi of t. And how do we do that? We just apply the evolution operator u upon the state vector psi of 0 at time 0. Its main physical interpretation of this is that it is an operator, the evolution operator, that does not describe an observable, that is, a measurement. The evolution operator is not an observable. It is something that evolves the state function. In fact, it is the evolution in time of a quantum system. It gives us the evolution in time of a quantum system. It changes the phase of the wave function or state vector, but not its length. Imagine a vector and you change the direction, but not the length of this vector. This, so to speak, length conservation, you conserve the length of this state vector, reflects nothing else than the necessity to conserve the sum of all the probabilities associated to the eigenstates before and after the state evolution. This can be expressed using the equation that we used in a previous slide. Remember this one, where the square, modulus square of the bracket of psi, that is the sum of all the modulus square of the coefficients, must give 1. Then we can generalize this expression from a time-independent, from this time-independent expression to the time-dependent expression. But the sum of all the probabilities must always be equal 1 if in our quantum system there is no interaction from the outside that destroys everything. But for an isolated quantum system that evolves in time, this expression must be conserved. And that means that we obtain this quantity here. Therefore, its name unitary operator, because it transforms something, but unity is conserved. Moreover, note that if u is a unitary operator that evolves the quantum state forward in time, its complex conjugate u star equal the Euler number power plus I ht over ih bar sends it backward in time by an interval t. Then it becomes obvious that applying first u star, the complex conjugate, and u consecutively, this means that it preserves the state. That is, it is an equal formal definition of a unit operator is that it satisfies the general relation u star times u equal 1, because you go forward in time, then you come back, and nothing has changed. Of course, again, this must give that this is the identity operator. It leaves everything identical, with 1 being a scalar, just a number 1, or more generally, an identity operator that leaves the things as they are. More we will tell on this later, because this concept of the unitary operator or unitary evolution, more generally, is a very important concept in quantum mechanics. As we will see, this operator reappears throughout our journey, and we will discuss its properties in different contexts again. For completeness, since we will make use of it when dealing with quantum decoherence, let us point out how once the Schrödinger equation has been solved and the eigenstates with its eigenenergies are known, it is possible to calculate the transition, so-called transition amplitudes, that is the probability that an atom transitions, say because of the scattering or absorption of a photon, from an initial state ket psi to a final state ket phi. Dirac's notation allows to determine the probability that this transition will take place as follows. Here you see the usual modulus square, and what is squared is the bracket of the state psi to state phi. So we have an expression in Dirac's notation of what the probability is that a state, typically an atom or a quantum system, transitions from a state psi to a state phi. And you express this with the Dirac's notation with this way. For example, the probability that an atom in isolation spontaneously transitions from an energetic lower eigenstate E0 to a higher one, E1, is 0, which implies that the bracket of E0, E1 equals 0. In this case, one speaks of orthogonal state vectors, because geometrically this is displayed as being the eigenstate vectors perpendicular to each other. That's, after all, the meaning of the eigenstates and their display in a Cartesian space, multidimensional space, where the axes have an orthogonal orientation, and if you make the scalar product of orthogonal vectors, you have always 0, which in quantum mechanical terms means that the probability to transition from one state to the other is 0. And that's why the eigenstates, when we measure them always, many times, they remain there. That's the real fundamental meaning of the eigenstates and orthogonality in quantum mechanics. However, for any quantum system which is subjected to an outside interaction, say such as in a scattering or a measurement process, an atom receives a photon or something like that, the state vectors may no longer be orthogonal. And this equation acquires a non-zero value and represents the transition probability from one state to another. There is then a certain chance that due to this interaction or measurement, a state transition occurs in case of atoms, eventually by emission or absorption of photons. This was just a brief introduction to the formalism of quantum mechanics. We will not go we will not dwell too deep into this formal aspects of quantum mechanics. I wanted only to make a short, brief, and a bit superficial overview of the subject, but it is necessary because here and there something will always pop up and it will be necessary to have at least an idea of what's about.